the energy of pi to px and pi to py is lower than sigma to pz. But in oxygen, sigma to pz is lower than pi to px and pi to py. Okay. So now I'll go for O2 molecule. Okay, so electronic configuration of oxygen atom. What is this? 1s2, 2s2, 2px, 2py, and 2pz. So it is 2, 1, 1. Okay. So now in this today, Miss Lapang is there. Miss Sharon Lapang is there or not? Hello.
No, sir.
And what about your friend? Sigma 2pz is lower than pi 2px. So let me write here. 2px, 2py, 2pz. 2py, sorry, 2pz, 2py, 2px. See, it should be symmetrical. And sigma star 2pz in both the cases is highest. Whether it is boron, carbon, nitrogen, or oxygen, fluorine, neon. Nice. This is sigma star 2pz. Let me finish after that you draw. Okay. So now this is this. So this is pi to py. Pi star to py. Then this is pi to px, pi star to px. Okay. So this is oxygen atom orbital, oxygen atomic orbital, oxygen molecular oxygen. This is called dioxygen. This is oxygen, this is called dioxygen. So oxygen atomic orbital, oxygen orbital, dioxygen molecular orbital. This is 1s, this is 2s. This is 1s, this is 2s. What is the electronic configuration? 1s2, 2s2, 2px2, 2py1, 2pz1. So 1s2, 2s2, 2px2, 2py1 ulta. So now how many we have? 8 plus 8, 16. अच्छा से देखो. Look at the screen now. 16. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See here. 11, 12, 13, 14. These two energy levels are again same. So it is 14, 15, 16. See, it has two unpaired electron in the pi star anti-bonding level. And that makes oxygen paramagnetic. Okay. So this paramagnetic behavior of oxygen could not be explained by valence bond theory. Okay. So now we are going to write electronic configuration. Electronic configuration of O2 molecule. Okay. So what you will get now here? Sigma 1s2. Sigma star 1s2. Sigma 2s2. Sigma star 2s2. Sigma 2pz. See now, these two energies are same. So within bracket we'll write. I know. This. Okay? These two. After that, what? These two again same, but these are higher than this. So write it like this. Pi star 2px and pi star 2py 1, 1. So this is the electronic configuration of oxygen molecule. What is magnetic nature? Magnetic nature, right? O2 is paramagnetic. So if this question comes in that case, you need not draw this one. You will write oxygen is paramagnetic, but why? Due to the presence of two unpaired electrons in anti-bonding pi orbital. Draw. আসেনি এখান থেকে তো দেখা যায় না রাস্তা যেতে হবে আমি তখন কোথায় We'll now go for fluorine. I told you oxygen, fluorine, and neon will have the same set of orbitals. Okay. So right now here F2 molecule. Okay. So fluorine is 9. So it is 1s2, 2s2, 2px2, 2py2, 2pz1. So we'll draw the same way. Fluorine atomic orbitals. Fluorine atomic orbitals. Yes. So now 1s2, 2s2, 2px2, 2py2, 2pz1. 1s2, 2s2, 2px2, 2py2, 2pz1. Okay. So 9 plus 9, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Achha, by mistake, I think I did not write here. This, no, please excuse me. Sometimes I forget also. It's not that I don't want to write. I want to write everything. In previous also, in your oxygen orbit, if I have not drawn, please draw it. Okay, this is for fluorine molecule. So what is this electronic configuration of F2 molecule? So here I will write 2p, pi 2px2 and tie 2py2. Now, no unpaired electron. So what will happen? It is dia magnetic. Oh, hey. In oxygen, I have not written the bond order. In oxygen, before you go for this, please write the bond order for oxygen. Bond order. Okay. So it is half NB minus N. So it was half 10 minus 6. So half 4. So bond order was 2. This is for oxygen, dear. Okay. So here I'm going to write bond order. Please do write it in oxygen, please. For fluorine, I'm writing bond order. Half NB minus N. So this half 10 minus 8. See here. 2 to 4. 6, 8. This 1. Magnetic nature. Para okay. So now This is neon. This is neon. This is neon. Only one thing that I'm going to do, I'm going to remove all the electrons. That you will now do by yourself. By copy and paste, you will not learn anything in your life. Orbitals will be the same orbital. So you must know how to fill up electron in both atomic orbital and molecular orbital. You will do it. After you finish, then you tell me, then I'll fill up and you will compare. This also you will write it. See, how do you do? 1s2, 2s2, 2px2, 2py2, 2pz. 1s2. Okay, so 10 plus 10, 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, same energy, 17, 18, 19, 20. So it is 1:2. See. This is called equivalent. This is this. It is Na2 molecule does not exist. Na2 molecule does not exist. Why? Because its bond order is 0. Okay. Compare. Is it all right? Compare that we have drawn. Have you compared? Arrange oxygen O2 plus O2 minus O2 2 plus and O2 2 minus in order of I told you how if you want to find out stability, you have to find out the bond order. To know the bond order, you must know the electronic configuration of the molecule. So first let me write. This one you have already written now. So what is the electron configuration of O2? We know sigma 1 is to sigma star 1 is to sigma 2 is to sigma star 2 is to sigma 2 pz2. So these are all in order of energy. Oh, sorry. This sorry. This is 1 and 1. Let you know. So let me write here O2 plus first. Let me find out the bond order. Series half 10. 2 plus 2 4. Sorry, 2 plus 2 4 plus 2 6 plus 2 8 plus 2 8. 10. Now, what are the number of electrons in antibonding level? 2 plus 2, 4. 5, 6. Then we'll write now here O2 plus. I always told you that the electron is lost always from the last energy level or added to the last energy level. See, last energy level is this or this. So you can remove from anyone because energy is same. I have removed from here, so I did not write anything. If you wish, you can write like this. 2p y0. Okay. So what is the bond order? Number of bonding electrons 10. Number of anti-bonding orbitals, it was 6, now 1 less 5. So it is 2.5. Let me write it here. See, now electron is added here. So I can put anywhere. Okay, let me put it here 2px. See, it was 1. So I'll add here, it will become 2. This is 1, it will remain 1. Ten. See here it is 10. Now I have added 1, so it will be 7. Okay, so it is half into 3. Okay, I'll write here. Half into 5 is equal to 2.5. This. O2 plus. See now, 2 electron loss. So both one here and one here, both of them will be lost. So nothing is there. Okay, see here. How many bonding electrons are there? 2, 4, 6, 8, 10. 10. Then anti-bonding 2, 4. Then O2 2 minus. It is 2 extra electrons are added. Now I have 2 electrons I have to add. One I can add here and one I can add here because we cannot have more than 2. This. Okay. So now see the bond order. Half NB minus NA. Then anti-bonding 2, 4, 6, 8. One. Draw. And after that, you will write it. Decreasing in order of. Please change the question. Decreasing stability means we have to write it from left hand side. See, we know that higher the bond order, more stable the species is. So what should I write now here? Which is having the highest bond order? O2 2 plus. Okay, it is 3. Then next is 2.5. Next is O2. Next is 1.5. Then next is this one. This is the one. Let others also do. Acha, now see, you are from different schools, so you will send me in this post-it in the group that what are the units or chapters which are being taken in your school. All of you will post it so that I should see what should I take in future. Okay, now we'll come to the almost to the last part of the chemical bonding. It's called hydrogen bonding. Hydrogen bonding. Please remember, hydrogen bonding is not the bond between two hydrogen. Okay. The electrostatic static force of attraction which exists between the covalently bonded hydrogen with highly electronegative elements like oxygen, like fluorine, oxygen, or nitrogen. I'll put this in bracket. Of one molecule, I'll explain. It's not that difficult. With such elements, of other molecules or groups is called hydrogen bonding. Hydrogen bonding is represented by dotted line. Its bond strength is almost 1/10 of a normal covalent bond. First, you write, then I'll explain. Why such bond occurs? See here. Say you have taken hydrogen fluoride. Fluoride is a very strong electronegative element. Look here. When the bond formation has taken place, covalent bond formation has taken place, okay, see, this is the nucleus of hydrogen. Okay, I'll write here now, H. And here you have the electron. And this is the fluorine. This is the fluorine. So this is the one. So after the formation of the bond, fluorine being the very strong electronegative element, fluorine pulls both the electron near it. See now. See. Now this hydrogen cannot find this electron nearby. Hydrogen cannot find this electron nearby. Then what happens now? Hydrogen is alarmed that hydrogen had one proton and one electron. Now this electron is being forcefully taken by the electronegative element like fluorine, oxygen, or nitrogen. So it is in dire necessity of electron. So in that case, what is going to happen? Where from is going to get electron? Now see here. See, this is the other one. When this electron is being taken, we know we have heard about polar bond. It has become now this. So in that case, hydrogen comes near to the electron-rich fluorine atom of another nature. And that way, the electrostatic force of attraction is being developed. All right, this electrostatic force of attraction is developed. It comes very close to it, and that is called hydrogen bonding. So instead of drawing this Lewis structure, how should we show hydrogen bonding? Okay, we show it like this here. This is the electrostatic force of attraction, which is being shown by the broken line. This is called hydrogen bonding. So hydrogen bonding will occur with extremely strong electronegative elements, but its sizes should be small. See here, hydrogen bonding is shown when hydrogen is bonded to fluorine, then oxygen and nitrogen. Hydrogen bonding is shown by hydrogen when it is bonded to very strong electronegative elements. Of small sizes like fluorine, oxygen, or nitrogen. See, why do I cut small size? This is for entrance. Both chlorine and wait, and nitrogen have almost same electronegativity, but chlorine does not. Exhibit hydrogen bonding due to its small size. Oh, sorry. Due to is larger size. Done.
Yes, sir.
Okay. Now we'll go for classification. Hydrogen bonding. One is intermolecular. And second one is intra. Please remember, intra means within, and inter means between or among. Okay. Now we'll go for intermolecular hydrogen bonding. When hydrogen bonding occurs between or among the molecules is called intermolecular hydrogen bonding. Okay, dear, see here. Hundreds of molecules of HF are associated with hydrogen bonding. So we'll write like this. Okay, so this is with HF. Now let me go for water. See. hydro here the lone pair hydro, huh? Sorry. Sometimes I make such funny mistake now. See, because lone pair is being given now. Like this. So here oxygen has two lone. See, this is also bonded to other molecules. I don't have space to draw. I'll draw it again separately for you. Huh? Don't. I don't never want that you should face problem. Okay. This is for water. Now, this is for alcohol. This. So I have shown with one with chlorine, one with oxygen, two with oxygen, because any of them may become. Then I'll show with one nitrogen here, ammonia. See here. See. See, this is again bonded to other molecules. This is again bonded to other molecules. Right. Today I'll take little extra time, huh? Please don't mind if you have class in school also, because I want to finish this chapter. Question may come. What is the maximum number of, write down the question. Okay. What is the maximum number of hydrogen bonding shown by water molecule? What is the maximum number of hydrogen bonding shown by water molecule? Very easy. First you draw water. Okay. These are two hydrogen, two lone pair. So please this see. This hydrogen will form hydrogen bonding with other molecules. This is going to show you hydrogen bonding with another. So 1, 2. And this is going to bind with okay. Sorry. So this is going to bind. This is going to bind. So how many are there? 1, 2, 3, and 4. This is first. This is the maximum number of hydrogen bonding you will find in the water molecule. Okay, so please remember for your entrance exam. Intramolecular. When hydrogen bonding occurs within the molecule, within the molecule with electronegative elements, chlorine, oxygen, or nitrogen. Present when hydrogen bonding occurs within the molecules with electronegative elements, chlorine, oxygen, nitrogen present. Is called intramolecular hydrogen bonding. Due to intramolecular hydrogen bonding, the molecules do not undergo association with other molecules. Earlier, we have seen hundreds and hundreds molecules are joined. Here, they do not undergo such. Molecules do not undergo other molecules and remain as individual. Okay. Example, say I have taken this. See here. This is ethylene glycol or ethane 1,2-di. See, just taken place within the same one. Then see, this is ethanol amine. Ethylene glycol. This is called ethanol amine. I am writing common name because IPC I have not taught you till now. This. Okay. Then see here. Look. This. This is called salicylaldehyde. This. This is called salicylic acid. This is called salicylic acid. Please give me 10 minutes time, please. See, hydrogen bonding are very weak, but hundreds and hundreds of such bond when it is present, total strength becomes very, very high. Okay. Now we'll see here. Influence of hydrogen bonding. First one is association. Due to intermolecular hydrogen bonding, large number of molecules are interconnected with each other. Okay, I'll write here now. Or associated with each other. For example, क्या होगा? See, we know so many molecules of water, sorry, each other are connected. So what will happen? You will find it is just like this. Water exists like this. Acetic acid. This is acetic acid. Molecules exist as dimer, means two of them are doing, both in vapor state as well as in non-polar solvents like benzene, CCl4, etc. See, how does acetyl molecule exist? Low. Ink finished. Okay, see here. See here. Two of them are connected with each other. So exists a dimer.
Yes, sir.
See, the questions will come from this portion. Now, second is melting and boiling points. Second, melting and boiling. Please remember, whenever you substance you boil, it goes to the vapor state. In vapor state, molecules always go as individual state. When you melt, the molecules separate from each other. So any substance having intermolecular hydrogen bonded, they require more energy first to break the hydrogen bond and to get separated. So their molecules having intermolecular hydrogen bonding have high melting and boiling points than those of intramolecular, because intramolecular they remain already in individual form. Molecules having intermolecular hydrogen bonding have higher melting and boiling points than those with intramolecular hydrogen bonding. Okay, now why? All right, it is because in intermolecular hydrogen bonding, numerous molecules are associated. So, in order to separate them, more energy in the form of heat is required. In case of intramolecular hydrogen bonded species, the molecules remain in individual form. So they are boiling and melting points are less. Please write it, then after that I'll draw the example, huh? Because it will get some space.
Sir, ladder.
Lande, wow, very good, very good.
No, sir.
Huh? Who told Lande?
Yes, sir.
Acha. So example, huh? This example generally the exam they give, huh? See here. Look. This one is see here. This is called ortho nitrophenol. See, this is called intramolecular hydrogen bonding. So the bonding is taking place within the molecule. Other molecules are not associated. So this melting point and boiling point is less. But if I go for paranitro, look, so many molecules are bonded with each other, huh? Okay, now Miss Sharon Lapang is there. That I could not find her.
Yes, sir.
Hey Sharon, if you don't understand anything, why you don't call me? Not only is for Sharon, for everyone. Huh? Yes, sir. See here, hundreds and hundreds of molecules are associated like this. Now, if you want to melt it, all this hydrogen bond you have to break. So you require very high amount of energy. So this is called para nitrophenol. This question may come. Next is influence on the physical state. Physical state. Right here, third. Compounds having intermolecular hydrogen bonding either exist in liquid or solid state. For example, it may come in the exam. For example, oxygen and sulfur both belong to same group, but H2O is liquid while H2S is gas at room temperature. Okay. This question will come. So what will write? Oxygen being more electronegative develops intermolecular hydrogen bonding in water molecules, and so exist as liquid. On the other hand, sulfur has poor electronegativity and does not develop any hydrogen bonding within them and exist as individual H2S molecule and is gaseous. Good, very nice girl. Alcohol, amines, carboxylic acids, carbohydrates, are soluble in water due to hydrogen bonding. Okay, see here, I'll draw. See, alcohol, water. See. So you can write here now. Alcohol, water, solution. Bye. Thank you. Acha, next day I'm going to start states of matter.